we will move on to the PMOS transistor. So the PMOS transistor, the structure is exactly the dual of your NMOS transistor, where I have diffusions which are P plus. Okay, these is my metal and oxide. The thickness will be the same for an NMOS transistor and a PMOS transistor, right? And this substrate is going to be N. Okay, so now I could have gate, source and drain, and this is my body. So now let's analyze the three cases. What happens when VGS is greater than 0? Case 1. 2. VGS is less than 0, and 3 we will come to that. So what happens when VGS is greater than 0? Yeah, you will attract positive charges here, right, and therefore you will get negative charges out here, right? Enough number of electrons and so on, you will get negative charges there, and which is again not very useful, and therefore this region is what you are basically accumulating more electrons at the surface than what is there in the bulk, and therefore this region now is called accumulation. Okay, sorry. So the interesting region of operation is when all these positive charges become negative, where VGS is going to be negative, and therefore I start depleting the channel, okay, which means I am going to drive away electrons and leave behind immobile right, I am going to leave behind immobile positive charges like this. So this will happen until the surface potential gets pinned, right, just like the NMOS transistor. So you will have a surface potential that develops across this psi s. Obviously VGS is less than 0, so psi s will also be a negative number, right. In fact, if for psi s is 0.25 volt for an NMOS transistor, typically this will be minus 0.25 volt for a PMOS transistor. Okay, this is the convention that we are following, right. You keep doing this, at some point you are going to attract enough number of free holes at the surface and then invert the channel. What does inversion mean? Strong inversion means that the concentration of holes at the surface is as much as electrons in the bulk, right, and then you apply your same derivation and you will get your current equation very nicely. The only important thing to note is holes are your charge carriers in PMOS transistors, while electrons were the charge carriers in NMOS transistors. So because holes are the charge carriers, current direction and charge direction is the same, okay. Charges always flow from the source to the drain, that does not change. It's only a direction of current that changes between an NMOS and a PMOS transistor. Okay, so my charge direction is from source to drain, and current direction is also from source to drain. I'll just say I, and this is my magenta is charge flow. Okay. So if you look at this now, compared to the source, what should be the nature of the voltage I apply on the drain side? Should be a negative voltage, because again current can flow only from high potential to low potential, that doesn't change. NMOS transistor or PMOS transistor, that doesn't change. If current has to flow from high potential to low potential and the charge and current flow from source to drain, then obviously the source should be at a higher potential compared to the drain, right? So this, for current flow, VSD should be greater than 0 or VDS should be less than 0. Okay. And by the way, just like the NMOS transistor, VGS less than 0 is depletion region, depletion mode, and VGS less than VT. You keep reducing the gate voltage, at some point you would have inverted the channel. That point is known as the threshold voltage. If you go further, then you are going to get more and more electrons at the surface that can constitute, holes at the surface that can constitute current, right? This is, what is this mode of operation? Inversion. Okay, and the convention here is already with, VGS. VGS should be less than 0. So clearly you are seeing a trend here that all quantities are becoming negative. Okay, yeah. No. So like I told you earlier, even for the NMOS transistor, if I give you just the device and ask you what is the source, what is the drain, I have no idea. You have to tell me what potential you apply. Once you apply the potential, in a PMOS transistor, the higher side is the source, because that is sourcing the charges and the drain is draining out the charges. It is just a convention and a definition. By definition, of course, if I can reverse this potential and apply higher there, by definition that will become the source, that's all. Okay, yeah. So it turns out that the drain current equation does not change. Okay, my IDS will be Kp prime, okay, W by L into VDS into VGS minus VT, I'll call it VTP if you want, minus VDS by 2. This is for linear. Okay, and saturation will be Kp prime W by L VGS minus VTP the whole square. Okay. Similarly, the equation for threshold voltage will also not change, it will just be VT naught P, right, plus gamma times root of, this is where the mod is important, because psi s becomes negative, you have to put root of mod of that. Okay, psi s plus VSB, again it doesn't change, minus root of mod psi s. Okay, and of course if I go ahead and now incorporate all the short channel effects, then this guy will become into 1 plus lambda VDS, lambda P into VDS, right? And then there is a gamma P also here. Okay, how many parameters do we have, right? And similarly, I cannot just keep increasing my, reducing my VDS negatively and achieve more and more current. You have a saturation velocity there as well, and therefore you have a VD sat P even in that case. Okay, so let me just write the unified current model for a PMOS transistor. IDS will be Kp prime W by L into V max. Okay, I'll tell you what that is. VGS minus VTP minus V max by 2 into 1 plus lambda P into VDS. Okay, this is obviously if VGSP or VGS is less than VTP. Okay, and it is 0 if VGS is greater than VTP. There is no current through the PMOS transistor if VGS is positive or has not yet inverted the channel. Okay, what is V max? Is simply going to be maximum of VGS minus VTP, VDS and VD sat P. Okay, I am not writing it in terms of mod because it's little bit confusing. Yeah. Where? No. So here I am not asked you to do any mod. VDS is whatever VDS value. If it's minus 0.2 volt, you substitute minus 0.2 volt in this. Yeah. You just put negative values. Exactly whatever, mathematically whatever this equation says, you just follow it. Okay, that's the idea. That's why I am not trying to write this in terms of mod, because that becomes confusing, especially when you bring in the threshold voltage and all that. Okay, so what we will do now is to simply compare what the sign of each of these parameters should be. We had 5 parameters that defined the level 1 spice model for the NMOS transistor. We have similar 5 parameters here. Okay, so I'll just write that on one side. K prime, what is K prime? Then VD sat, right? Then lambda, then VT naught and gamma. These are the 5 parameters for the level 1 spice model. We had 2 transistors, Nmos, PMOS. Okay, and let me also write the threshold voltage equation here. VTH is VT naught P plus gamma into root of mod VSB plus psi S minus root of mod psi S. Okay, and there is a gamma P here. So in an NMOS transistor, all these parameters were just positive. Okay, we understood why each of these parameters, for example, why gamma should be positive, because if you increase VSB, threshold voltage should go up, right? And therefore gamma has to be a positive number, right? On similar lines, I want to analyze for a PMOS transistor what these values should be positive or negative. Exact value I am not worried about. Okay, so let's start with VT naught. It should be a negative value, right? Because as I lower my VGS, at some point I am going to invert the channel there, right? So therefore this has to be a negative value. What about VD sat? Negative value, right? Because the current will flow only if VDS is negative, right? And therefore that also has to be even the saturation value has to be a negative value, right? These are pretty simple ones. Now, what about lambda? What should happen to lambda? What should be the effect of lambda? Huh? Positive. Huh? Why? Okay, if it's positive, you tell me why it should be positive. If it's negative, tell me why it should be negative. Yeah? Negative, because VDS has to be negative, only then you'll have current, and with some lambda being introduced, that current should go up. That's what you want. If the channel is brought closer, then the current, mod of the current should go up, the magnitude of the current should go up. But that can happen only when VDS is negative. Remember, this is just a convention. The drain source voltage has to be negative, only then it can be, you can have a current, and therefore lambda also has to be a negative number. Why? Because this is a negative quantity. Only if this is also negative, this 1 plus lambda VDS will be a positive term that increases the magnitude of the current. Are you following me here? Right? What about K prime? Yeah? Positive. So remember, I just look at the equation I wrote very carefully. I wrote IDS equal to something. I did not say ISD equal to that. If IDS is equal to something, what should it be? Negative, because the current will flow from source to drain. But I am looking at IDS, therefore it's not a physical thing where this term has to become negative. Just to make my ISD IDS, my K prime has to be a negative number. Right, and therefore this also will be a negative number. Okay, we have solved 4 parameters pretty simply. What should happen to gamma? Why? So let us go back to our for it to, it should come. Yeah, but what is decreasing threshold voltage? No, but decreasing threshold voltage for a PMOS means what? Decreasing mod of the threshold voltage? Yeah, or I am increasing, I am adding a delta to the VT, right? But you are right, it's basically decreasing the mod of the threshold voltage. It is easier to invert the channel if the body is negative. Right? Correct? So if VSB increases, what should happen to the VTH of my PMOS transistor? Or what should happen to the mod VTH? Let's ask a simpler question. It should decrease, right? VSB goes up, VTH mod VTH should decrease. You agree? All of you agree with this? It's opposite of an NMOS transistor. If VSB goes up, the threshold voltage for an NMOS goes up. Right? But for a PMOS transistor, it should, mod of the VTH should come down. What does mod of the VTH come down mean? So in this equation, let's say this is minus 0.25 volt or minus 0.3 volt. Okay, then plus gamma P into something. VSB is going up. If VTH has to, mod VTH has to come down, what should happen to this second term? It should be positive, right? Yeah. So root of mod VSB plus psi s minus mod psi s. This should be positive. So if VSB goes up and gamma P into that term has to be positive, what should be the sign of gamma P? Yeah? Why? That is the catch here, right? It may appear, for example, that VSB, if VSB goes up, root of mod of VSB plus psi s also goes up. That's not true, because psi s itself is a negative value. Okay, so the way you should analyze this equation is write this as Vt naught plus gamma P into, let's substitute a value for psi s, minus 0.25 plus VSB minus root of mod minus 0.25. Okay, Vt naught plus gamma P into, this will become, what is it, 0.25 minus VSB. I am assuming VSB is less than psi s, mod psi s. You cannot arbitrarily increase VSB beyond 0.25 volt, 0.3 volt and all that. Some small deltas is acceptable, minus 0.5. So now if VSB goes up, then what is happening to root of 0.25 minus VSB? It's becoming less. That means this term will become negative. If now gamma P into that term has to be positive, so that the VTH actually comes down, mod of VTH comes down, implies gamma P has to be less than 0, and therefore this also has to be a negative quantity. This is very nice because all positive terms, parameter values for NMOS transistors, all negative parameters for PMOS transistors, but you should know why they have to be negative. And there are some catches like this, especially for PMOS. Substitute values and remove the mod, otherwise that analysis will go completely wrong. Okay, I will leave it to you as an exercise to go back and try out what happens, how you can do this backgate analysis. If you apply a body voltage which is negative, what should happen to the threshold voltage, all that. Just try it yourself and see that the equations tie up now. Okay, as an exercise. If you have any doubts, we can discuss it in the next class. Okay. So any other questions with regard to the PMOS transistor here? Yeah. Yeah. Correct. So you have to consider the maximum of these voltages, which is for the negative. Yeah. No, not magnitude. Absolute value. Not absolute, the value, actual value. So you are going to do, if I substitute your values, it will be max of minus 1, minus 1.2. Let's assume that this is minus 1.5 or something. VGS minus VT, right? Which is the maximum in this? Yeah. That's the value that you have to take. Okay, or you have to do min of mod of all these values. Okay, but I think that is actually very dangerous. Better deal with actual numbers. Okay. So let us look at a few plots. IDS versus VDS. In which quadrant will the PMOS current be? Which of the 4 quadrants will the PMOS current exist? The third quadrant, right? VDS has to be negative and IDS is also a negative number, right? And therefore, these plots of is, if VGS is not enough to turn on the transistor, obviously the currents will just be 0. No big deal about that. As you start increasing VGS, you will have this kind of a current, right? And if I increase my VGS slightly further, then it will remain, it could be in saturation region for low VGSs. For low VGS values, it could be in saturation. It need not go into velocity saturation mode. But beyond a certain point, of course, everything will enter velocity saturation and it will start looking like this. Okay, this is small VGS. Small VGS, of course, less than VTP, only then it will conduct, right? These are large VTs, large VGS, sorry, and it can get velocity saturated, right? This will end up in saturation region. Okay. Similarly, you can plot the ID versus VGS. Again, that will be in the third quadrant. Okay. So your question really will be somewhere here. This your VD sat, right? Magenta. What is the color I have not used? This will be your VD sat value. Your VD sat P will be somewhere here, right? And if your VDS is large enough, that means it is negative, then of course the current will be somewhere here in this particular region, which gets determined by the VD sat P. Okay, so that equation I have written there is mathematically consistent. Just substitute the values and you will get the answer. Don't do any conversion from mod, this, that, nothing. Okay. Which one? This one. This is VD sat. Because at the saturation value, it is, the current is saturating, right? So you look at the corresponding currents for the Nmos transistor that I draw here, right? The magenta is, again, it can be in saturation, right? Then and this will be your VD sat, right? N. The current is saturating at a particular VDS value. It doesn't increase any further, which depends on your VGS value also. If it saturates earlier, then that will basically dominate and you will get a saturation current. Otherwise, you will get a velocity saturated current. Clear? Not convinced? Why? You agree with the that is VD sat, yeah, velocity saturated drain source voltage. The drain source voltage at which the current becomes velocity saturated. Okay? To just finish corresponding thing, this is small VGS greater than VT and it enters saturation region. This guy is large VGS greater than VT and it enters velocity saturation. And of course the slope is basically your because of lambda p, right? Clear? Okay.